Everyone thought the future of computing was quantum. Then, Canada quietly built something that made a lot of very expensive assumptions look wrong. For more than 2 decades, the smartest institutions on the planet agreed on one thing. The next great leap in computing would come from quantum machines. Governments poured billions into it. IBM built quantum processors. Google claimed quantum supremacy. Nations launched national strategies around it. And for a long time, if you questioned that trajectory, you were the one who sounded naive. Then a group of Canadian researchers started asking a completely different question. Not how do we build a better quantum computer, but what if certain problems never needed quantum at all? To understand why that question matters, you need to understand why quantum computing became such a big deal in the first place. The short version is this. Classical computers, the ones running everything from your phone to the stock market, solve problems by going through possibilities one step at a time, or in parallel batches, but still in a fundamentally sequential logical structure. Quantum computers work differently at the level of physics itself. They can exist in multiple states simultaneously, a property called superposition, and they can link particles together in a way that lets them process certain calculations exponentially faster than anything silicon can do. For problems like cracking encryption, simulating molecules for drug discovery, or optimizing systems with billions of variables, quantum seemed like the only path forward. Governments and corporations believed whoever got there first would control the next era of computation. That belief was worth hundreds of billions of dollars in investment. But here is what was not in the press releases. Building a working quantum computer at commercial scale is one of the hardest engineering problems humans have ever attempted. Quantum systems require temperatures colder than outer space, colder than minus 270 degrees Celsius to keep qubits stable. Even then, those qubits degrade within microseconds. A single vibration, a stray electromagnetic field, even background radiation can destroy a calculation. The technical term is decoherence, and it is not a problem researchers are close to solving at scale. Error correction in quantum systems requires thousands of physical qubits to represent a single reliable logical qubit. That means a machine powerful enough to do something genuinely useful at commercial scale would need millions of qubits operating in near-perfect harmony inside a refrigerated environment the size of a small building, drawing enormous amounts of power and costing an amount of money that most corporations cannot justify outside of pure research budgets. That is not a criticism of quantum computing. The science is real, the potential is real, but the gap between laboratory demonstrations and machines that a logistics company or a hospital or a bank can actually use is measured not in years but in decades. And most honest experts will tell you that privately, even when they do not say it publicly. That is the crack in the foundation that Canadian researchers decided to walk through. The work came out of Photonics Labs in Canada, and what they built is called the Cascade Modular Ising Machine. The name sounds like something out of a science fiction film, but the underlying idea is surprisingly elegant. Instead of trying to manipulate quantum particles, the researchers asked a different question. Many of the hardest real-world problems are optimization problems, finding the best route through 1,000 delivery stops, allocating bandwidth across a mobile network during peak hours, scheduling a factory floor with hundreds of constraints. These problems share a mathematical structure, and that structure maps onto something called the Ising model, a framework from physics that describes how systems find their lowest energy state. Here's the intuition. Imagine you were trying to arrange magnets on a board so that as many neighboring pairs as possible are aligned. There are so many possible arrangements that trying them all would take longer than the age of the universe. But a physical system made of magnets does not try all combinations. It simply settles. It flows toward the lowest energy configuration naturally. The Cascade Modular Ising Machine does something analogous, but with light pulses moving through fiber optic hardware. It encodes a problem into optical signals, runs them through a cascade of modulators and feedback loops, and the system physically converges toward a solution the same way a physical system finds equilibrium. Why does that matter? Because the hardware it uses is not exotic. It is not cryogenic. It is not quantum. It is built largely from components that already exist in telecommunications infrastructure. The lasers, the modulators, the fiber delay lines, these are the same technologies that carry internet traffic across the planet every second of every day. That means the machine operates at room temperature. No cooling systems the size of a house. No vibration isolation chambers. No $1 million dilution refrigerators. And the report reported performance numbers are striking. The Canadian team published benchmark results showing operation at 200 billion operations per second for certain optimization problem classes, numbers that outpace what comparable quantum annealing systems have demonstrated on similar tasks. Now, before this starts sounding like a press release for a miracle machine, this is where the investigation gets more complicated. The comparison to quantum computers requires precision. The Cascade Modular Ising Machine is not a universal computer. It cannot run arbitrary algorithms. It cannot simulate quantum chemistry. It cannot break encryption. The problems it solves well are a specific family, Ising and Cubo problems, which stands for Quadratic Unconstrained Binary Optimization. That family is large and economically important, but it is not everything. Quantum computers, particularly gate-based machines from IBM and Google, aim at a much broader computational universe. Comparing them directly is a bit like comparing a Formula One car to a cargo ship. Both are impressive, neither replaces the other. The more honest comparison is with quantum annealers, particularly the machines built by D-Wave, a Canadian company, ironically enough, which have been commercial for years and also target optimization problems using quantum effects. And here, the Canadian photonic machine does appear to hold real advantages. It operates at room temperature where quantum annealers require extreme cooling. It can handle dense, fully connected problem graphs where D-Wave systems face a significant limitation because their qubit architecture forces an embedding overhead that inflates problem size and degrades performance. For certain classes of optimization, the photonic approach appears meaningfully faster and dramatically cheaper to operate. Think about what that could mean in practice. A major airline optimizing its entire flight network, gate assignments, crew schedules, fuel loading, and delay cascades simultaneously. A power grid operator balancing renewable generation across thousands of nodes in real time. A pharmaceutical company searching combinatorially through molecular configurations. A defense contractor optimizing sensor placement across a theater of operations. A city traffic authority rerouting 10,000 vehicles around an accident in under a second. These are not hypothetical applications. These are problems that already cost industries enormous amounts of money every year because existing computers cannot solve them optimally. The Cascade Modular Ising Machine is not guaranteed to solve all of them, but it enters those conversations in a way that no affordable room temperature hardware has before. There is also a less obvious connection to artificial intelligence worth considering. Modern AI training runs on GPUs, graphics processing units made primarily by NVIDIA, which are exceptional at dense matrix multiplication, the mathematical operation that underlies neural network training. The photonic Ising machine does not replace GPUs for that workload. It cannot. The physics are different. But AI systems increasingly encounter discrete optimization problems at their edges: hyperparameter search, neural architecture search, combinatorial reasoning, certain planning tasks in robotics and autonomous systems. There is a real possibility that photonic accelerators become co-processors in AI pipelines, handling the combinatorial subproblems that GPUs handle poorly and quantum systems cannot yet handle reliably. So is this a revolution? Here's where the skeptics deserve a fair hearing. Laboratory demonstrations are not products. The benchmarks the Canadian team published are real, but they were run on curated problem instances designed to showcase the architecture's strengths. Real-world problems are messier. They have constraints that do not map cleanly onto Ising formulations. They require pre-processing and encoding that adds overhead. The manufacturing of photonic systems at commercial scale involves supply chain challenges that silicon fabs have spent 60 years solving. The software ecosystem around Ising machines is nascent compared to the tooling available for GPUs or even quantum platforms. Researchers at institutions like NTT in Japan and Stanford have done rigorous comparative work on coherent Ising machines and quantum annealers, and the consistent finding is that performance is highly problem-dependent. There is no architecture that wins universally. And commercialization of deep tech hardware has a long history of promising laboratory results that took a decade longer than expected to reach markets. The honest assessment is that the Cascade Modular Ising Machine is a serious piece of scientific and engineering work that demonstrates a real alternative path for an important class of problems. It is not a quantum computer killer. It is not the end of quantum research. What it is evidence that the computing landscape is becoming more diverse, not less, and that betting everything on a single technological horse was always a questionable strategy. And that might be the most important thing this machine reveals. Not the machine itself, but what its existence tells us about the next 20 years of computing. The era of one dominant paradigm, first mainframes, then personal computers, then cloud, may be giving way to something more complex. A world where quantum processors handle molecular simulation and certain cryptographic tasks, where photonic Ising machines accelerate optimization across logistics and energy networks, where neuromorphic chips model biological systems, where GPUs continue to train the neural networks that increasingly mediate every digital experience. Not one winner, a mosaic of specialized hardware, each solving the problems its physics is best suited for. The question worth sitting with is this: if the future of computation is genuinely heterogeneous, which companies, which nations, and which research programs are building for that world? And which ones are still waiting for a single quantum breakthrough that keeps moving further into the future? Think about that the next time you hear someone say the future of computing is quantum. It might be, but it might also be something built from fiber optic cable and light pulses in a Canadian lab, running at room temperature, solving problems that billion-dollar quantum machines are still struggling to reach. The future has a way of arriving from directions nobody was watching. For more on the technologies and decisions reshaping the world you live in, make sure you are subscribed so you are not caught off guard by what comes next.